Up till now, we've looked at the equation of thrust and the exhaust velocity with respect to specific impulse. And we've also looked at how the propellant fraction and the inert fraction relate back to the total mass of our rocket. So now I'd like to take some time to derive the ideal rocket equation, the rocket equation in free space. And we're doing the ideal rocket equation in free space just to save some time, because if we were to do it in atmospheric conditions, we would have a few extra variables, not too bad. Now, the first step to deriving the ideal rocket equation is our handy friend, the thrust equation. Now, the thrust equation said that force is equal to the mass flow rate times our exhaust velocity. Now, we need to specify a direction now in our force equation. We can either do this by vector or by sign notation, and we can do it by sign notation in this case. So we'll say force is equal to negative m dot times the exhaust velocity. And again, the mass m dot is the mass flow rate, which is just the amount of mass of propellant which is spewing out of the nozzle every second. And the exhaust velocity is just how fast that propellant is moving. So we can rewrite our force equation, this equation down here, and we can say that force is also equal to mass times acceleration. Now, what we can say here is that m dot is a rate and acceleration is a rate. So we can write both of these in terms of their differentials and their time. So we can say that negative exhaust velocity multiplied by the differential of mass over the differential of time is equal to mass times the differential of velocity over the differential of time. Now, again, note that m dot and dm over dt, or a and dv over dt, are the same exact things. We haven't really changed, we've just substituted. So now what we can do is cancel some variables out. Our dt's are on both sides of the equal sign, so they can go away. And what we're left with is the negative exhaust velocity times dm, which is equal to the mass times dv. So let's get the mass all on one side, and we can do that by dividing both sides by mass. And what we end up with is negative exhaust velocity multiplied by 1 over m times dm, which is equal to our dv. So let's integrate both sides of this equation, since we have a differential in both sides of our equation. And we'll integrate it from the initial state to the final state. The initial state, so the initial mass and initial velocity, to the final mass and final velocity. So what we get here on the left-hand side, when we do this, we get the negative exhaust velocity multiplied by the natural log of the final mass subtracted by the natural log of our initial mass, which is equal to the final velocity minus our initial velocity. Now what we can do here, we can multiply this subtraction sign, we can move the subtraction sign in essence into these parentheses. When we do that, we're going to get an exhaust velocity multiplied by the natural log of the initial mass minus the natural log of the final mass, which is equal to the final minus the initial. In terms of science, we can write that as the change in velocity instead of just writing final minus initial all the time. We can write that as change in. This triangle represents change in velocity. And what we can say here, we can simplify this natural log function as well. We can say that anytime two natural logs are subtracted from each other, we can just say that the exhaust velocity multiplied by the natural log of the initial mass divided by final mass is equal to the change in velocity. And this is one of the most useful versions of our rocket equation. This is method or version number 1. Now we can get a second version of our rocket equation by dividing both sides of this equation by our exhaust velocity. So I'll do that down here. Let me scroll down a little bit. So what we get here, we get the natural log of our initial mass divided by our final mass is equal to the change in velocity divided by our exhaust velocity. And just to point out something, this change in velocity is the change in velocity of the entire rocket, not just the nozzle or the propellant. The exhaust velocity, on the other hand, is the velocity of the propellant only. So let's continue with this. Just wanted to clarify that. Now since we have a natural log on one side, we can exponentiate both sides of this equation to get rid of our natural log, and we end up with, we can write it over here, we end up with the initial mass divided by our final mass being equal to E to the change in velocity of the entire rocket divided by our exhaust velocity. And this is also a very, very, very important version of our rocket equation. This is the second version of our rocket equation. And since we have two versions of our rocket equation, we can actually do an example very quickly of our rocket equation. And in this example, I'll be using the first version. So the SpaceX Falcon 9 rocket, in the first stage of its ascent, the initial mass, let me do this in a separate color, let me do this in lime green. The initial mass is equal to 531,020 kilograms, and the final mass of this rocket after the propellant has burned is equal to 135,320 kilograms. And we know that the exhaust velocity, the calculated exhaust velocity of this rocket, is equal to 3,050.91 meters per second. So we can calculate, so we have our initial velocity, our initial mass and our final mass, and we have a exhaust velocity. So we can calculate our change in velocity of this rocket, of this specific rocket. So the way we do that, we can write our exhaust velocity multiplied by the natural log of our initial mass minus our final mass divided by our final mass, being equal to our change in velocity. So let's get our calculator out and we can actually plug these numbers in and find out an answer. So our initial mass was 531,020 kilograms divided by our final mass, which is 135,320 kilograms, which gives us 3.924. And we can put this to the natural log and multiply it by 3,050.91, which was our exhaust velocity. And this gives us a change in velocity of 4,171. This gives us a change in velocity of 4,171 meters per second. And this is how fast the entire rocket is moving. In the next video, I'll focus a bit more on these examples and we'll get to multi-stage rockets, which the Falcon 9 is a multi-stage rocket. See you then.